Welcome to part 4 of our lectures on graph learning. So we have still the part where we want to talk about an application, which is application query embedding. So this presentation was made by Daniel Daza. So he's my PhD student, and we worked on a work where we applied this relational graph convolutional networks to solve a very difficult problem. So we discussed already about what knowledge graphs are. So I'm going to keep this very short. So basically what we have this knowledge graph, so a graph with all kind of information about it, for example, medicine. And this is very useful for storing information. But what we now want to do is we want to answer questions about things in this graph. So what we have here is, for example, this graph here. And what this graph has is basically has a university. It has two people who work at that university. Then there are two projects, right? So these two projects which happen to involve these two people, and one of the projects is about machine learning. What we can now do is we can use a language called Sparkle, and what you can do with that language is answer queries like the one which is here. So you can basically select or give me all the projects which are related to machine learning on which Alice works. So basically, the answer here is project 1, right? So Alice works on that project. That project is related to machine learning, and so you find the answer. Now the question is whether this answer is complete. And of course, if you look at the graph, the answer is complete. But the point is that project 2 might also be an answer. So because you can see that both Bob and Alice work on both these projects. Project 1 is about machine learning, so maybe project 2 should also be about machine learning. So what could be the case is that there is basically a link missing between project 2 and machine learning. So it's just forgotten it's a missing edge in the graph. And so what you could do, we could use techniques which we talked about before, so the things about link prediction, and basically try to predict this link. Right? So we saw, of the examples mentioned here, we saw trans-E, which tries to maximize the scores of existing edges and minimize scores for random edges or wrong edges, and try to predict these missing links. Now, this is not really ideal because you have to do a lot of work. So for example, let's sort of extract this query a bit. So basically we want to select all the topics T, where T is related to a project P, and Alice and Bob basically work both on the project P. And now the problem is here that if we want to use a link prediction here, then we have to enumerate all possible pairs T and P, right? So we have to sort of look at all pairs of nodes and check maybe there is a missing link here, maybe there is a missing link here, and so on. So this number of missing links basically grows exponentially. And of course, that would not be a problem if we have a small graph, but the graph which you see here on the left is a small subset of, for example, Wikidata, and Wikidata is an example of a very large graph. But still, this kind of graph is not something which you can feed into these link prediction systems. Now, the realization for this paper is that when we look at queries, so the thing which we had written down, for example, here at the top here, that they're themselves also graphs, right? In particular, if we have what is called the basic graph pattern, so a simple type of graphs, a simple type of queries, and let's try to create such a thing. So we have all the topics T, right? That's what we are looking for. That's our target node. That's the target variable which we want to solve for. Where T is related, so that should be to a project P. And okay, so I quickly corrected that. So T is related to project P, and both Alice works on P and and Bob works on that project P. So we want to find all these topics. Now, so basically what we are doing in this work is that we are taking that query, which is a graph, and we are feeding this through a query encoder. Now, we will see in more detail how that works, but the way that you can think about is that query encoder works like an RGCN as we saw before. Now, what we have in this system is that for each of the nodes, these nodes here in this network, we have an embedding. So I'll move this one a bit. So we have for each of these an embedding, and these embeddings are just vectors representing these entities in the graph. Now, these embeddings are things which we are going to train, right? So initially they're just initialized randomly, and then we are going to start training. So what we do is we take as an input here, so we know in the query we have Alice and Bob, so they occurred in the query, so we immediately put their embeddings as an input to this graph convolutional network which we're going to build for this. Then we are going to encode that query. We are going to get an output for that encoded query, and now that output is something which is in the same space as these embeddings of the entities. Then inside that space, we perform a nearest neighbor search. So we take this embedded query, then we look at in that space what is here the nearest entity, and that we will declare as the answer. And so the cool thing here is that these vectors, so these embedded vectors, both serve as an initial input to your network, and later on serve as the space in which you're going to search for answers. Okay, so how does this query encoder work? Well, basically, they are graph convolutional networks, right? So actually relational graph convolutional networks, because these are typed, these edges. And basically, they are passing on messages, right? So we saw this before, like we had these states of the vectors in the nodes, and they're also called messages. So we basically said they pass messages through the network. And in this style, which we call message passing query embedding, we learn those embeddings here, which we talked about, but we also learn these weights which we are putting on the edges in our relational graph convolutional network. So these are basically two learnable parameters, right? So it's both the entity embeddings are learned and the weight matrices, but also for the variable nodes, we are learning an embedding, right? And the variable nodes are this P and D, because they are not actually entities which exist, right? So they are not bound to anything yet, but still we learn an embedding for them. Then after this initialization, right? So we can see it here on the right. So we have this unrolled network here now. So this is initialized with these embeddings which we have. This is initialized with the embeddings for variables. Then we start propagating the network, as we saw with the relational graph convolutional network. And in the end, we get an embedding for each of the nodes. And that's not exactly what we wanted, because what we need in the end, as you could see in our overview here, is just one embedding. But what we are ending up with in this network is we are ending up with one sort of encoded thing for each of these nodes. So what we're going to do is we're going to still combine that into a smaller form. So the way this roughly works, that this gets propagated, and then we have to combine this still into one query embedding, right? Because at the end we have an embedding for everything rather than just one overall query embedding. So what we basically do is we are going to take all these embeddings, and we're going to map all these final states into one embedding for the query. But there are a couple of things which we want. We want this thing to be permutation invariant, basically meaning that the sort of shape of this graph or the order these nodes are, whether you take Alice first or Bob first, shouldn't matter because they're sort of the same. They don't have there's no preference in their ordering, basically. There are a couple of options. So the simplest form is basically that we just take this target node. So we take this embedding as our query embedding, and we are done. Right? So we ignore basically whatever is on the other ones. Now we can also do more complex things. So we can take these four embeddings, right? So these are these 1, 2, 3, 4 things. I see one of the colors has changed, but these are the same things, and aggregate them in this one vector. And so here are different ways on how this can be aggregated. So you can sum them together. You can do sort of max pooling. You can apply a big MLP on all these 4 things and squash it into one representation. And you can do a couple more versions of that. So, yeah. And the question is, so why is this a good idea, right? So, now the thing is actually that the way we are doing this makes query answering very, very scalable. right? So because what we do is we have a query encoder now, which works very efficiently. It's actually sort of the complexity is just in the size of the graph. So the number of, you give a number of steps, the number of message passing steps, but the number of messages you forward each step is just as many as you have edges in your query. Queries are typically not extremely big. They are typically small structures. Then the most expensive part of the query answering system is the nearest neighbor search, right? So here this is in a linear time because we don't do any approximation, so we just do a linear search over our space. Now this is very good because, as we mentioned before, in a normal query answering system, this step, so if you would be using a link prediction, this would be exponential. So now we can do this in a linear time. It actually becomes just feasible. Okay, and then the other cool thing about MPQE is that it's able to encode arbitrary queries, right? So you can do any shape of query, not just not just lines or not just any kind of simpler things. So then we have an evaluation, right? So we what we do is we basically have this graph, right? So we have the original graph, and to evaluate it, we need to ask a lot of queries. We need to see that it's able to solve all sorts of queries. And so what we do is we are going to sample subgraphs from that graph and then replace some of the entities by variables, right? So we, for example, have here all this PT, so that comes basically from this subgraph here, which we extract first, and we replace this by a variable and this by a variable. We could do a similar thing. We have Alice and Bob PT, so that's basically this subgraph which has been extracted and so on. And so this way we extract a lot of subgraphs. Now, one thing I should mention here is that when these subgraphs are basically extracted for an evaluation, then we do it such that for the training of the system, we remove even more edges. That means, like, for example, if we have this query as an evaluation query, we're going to take one of the edges here, let's say this one, which corresponds to that one, and we're going to remove it in the graph before we do any learning on that graph. So this way we avoid having this problem where you have basically a leakage from your test set to your training set. So that's basically queries for training obtained after dropping this some edges, which is mentioned here. So we evaluate this on 4 different graphs. So they are not extremely large. So they are like, well, let's say from 2000 to about 300,000 entities, up to 8 million relations in it. And basically, what we did is we selected certain shapes of queries, right? So these were also used in previous literature, but they actually cover a lot of cases, basically cover every case where you have up till 3 hops in your query. 3 hops, and I mean basically your graph would contain 3 edges. And now the cool thing which we could do is, like, we have a training. So in the previous work, right, what you always would see is you would have a training step in which they use all these 7 structures and then evaluate on these 7 structures. That's sort of, okay, yeah, you can do that. But what we could do here, which is the really exciting part, is that we could train on just one chain query. So we train on the simplest case, right? So it's just one hop, nothing more. And then evaluate on all these more complex queries. And so what is exciting about that is that if this works, right, so we can go from one just very simple training of very simple things that we can evaluate, or we work well on all these structures. It basically means that this could potentially also scale to all possible queries which are out there. And so what we see is that well, this is for the all query types. So our system works reasonably well, outperforms, or at least comes to par with existing systems. But more exciting is this part on one-chain queries, right? So one-chain queries means you train on one hop and then you evaluate on all the other structures. And what you see here is that we actually perform very well and typically outperform existing systems, except for certain types of graphs. So this is very exciting because it means that we can train our system on just this one hop things, and we can actually evaluate on queries which go very much further. Another very nice property of this method is what kind of representations are learned, right? So there is a previous method which was trying to solve the same problem. And if you just plot the embedded space, right? So we have these embeddings for the entities and we colorize by type. So purple would be, for example, all the projects. Then And we notice that it's a bit clustered here and there, but it's not very nicely separated. While in our space, what you can see here is that you nicely see separation, that this would be all the people, this would be all the projects, this would be all the topics, and you see nice clumps of these things together. So that means that our space has more semantic information about them, so it's more navigable, as we discussed in earlier parts. So in conclusion, what we have is a sort of is an architecture which was based on RGCNs, the thing which we saw before. It's rather simple. It can learn entities and type embeddings, which are useful for solving the task of query answer. Then it can basically solve questions for any BGP, so that means basically like this kind of graph-shaped queries. Message passing algorithm basically has superior generalization, meaning it can just train on these one-hop queries and go to much larger ones. And as we could see in this visualization, we could also capture the notion of entity types without any specific supervision, except the signal which was originally, which is basically coming from the queries. Okay, so this was the example or the application of RGCNs. So one example worked out. So what we did in the whole series of lectures now, or all the parts, is first we had an introduction. So we looked at why we want to work with graphs and what embeddings actually are. Then we discussed on graph embedding techniques, the more traditional ones, where you would basically do first an embedding of, for example, nodes, and then use them for a downstream machine learning task. Then we looked at graph neural networks, which are used for end-to-end learning systems. And finally, we looked at an application of this relational graph convolutional networks when we were talking about the query embedding. Thank you.